Fermat's theorem says that if the function f of x has a relative extrema at the point x equals c, and the derivative of f at the point c exists, then the derivative of f at c is 0. Let's take this example here. This function has a relative extrema at x equals c. That means if we take any open interval that contains the point c, then f of c will be greater than or equal to f of x for all x an element of this open interval. I'll call the interval L. Now this happens to be a relative maximum, but of course we could be talking about a relative minimum. Also you can see that at x equals c the curve is smooth, so the derivative of f at c exists. If we had a sharp corner at x equals c, suppose our graph looks like this, then the derivative at this point would not exist. We could not construct a tangent at this point. We could have infinitely many such tangents, if you want to call them that, but there's only one tangent to the curve at x equals c here, because the curve is smooth. Okay, so that means then, from Fermat's theorem, that the tangent at this point is horizontal. Its slope is 0. F prime of c is 0. So that's what we're going to prove. Okay, we are going to assume that the relative extrema at x equals c is a relative maximum. The proof is nearly identical for the case of a relative minimum at c. Now for values x close to c, f of c is going to be greater than or equal to f of x. That makes sense. So at c we have a relative maximum. So for any values x close to c, obviously f of c is going to be greater than f of x. So that means if h is close to 0, close enough to 0, then f of c is going to be greater than or equal to f of c plus h. So rather than referring to f of x here, we could take this value to the right of c, or close, which is close to c, as c plus h, and the value to the left as c plus h also, but in this case h would be negative. Okay, we'd be subtracting a certain amount from c, and then you can see that f of c plus h takes the places of f of x. That's less than f of c, whether we're talking about the point to the right of c or point to the left of c. As long as we're dealing with a small enough neighbourhood of c, f of c will be greater than or equal to f of c plus h. Now let's rearrange this, subtract f of c from both sides. Now we are going to construct f prime of c, and to do that we need to divide this quantity by h. Now h can be either positive or negative. At this point we will assume that h is positive. So we divide the inequality by a positive quantity. It doesn't change the direction of the inequality. Now we take the limit as h tends towards 0 of both sides of this inequality. Since h is positive, we are really taking a one-sided limit. The limit as h approaches 0 from the right. Now we are given that f prime of c exists. To calculate f prime of c, we would take the limit as h tends towards 0, either from the right or from the left. Both limits have to exist. For the limit as h tends towards 0 of this quantity to exist, it must be the case that the limit as h tends towards 0 from the right will be equal to the limit as h tends towards 0 from the left. And those two limits will equal this limit here. That's the condition for a limit to exist. In this case the limit is f prime of c. Now what is the limit as h tends towards 0 from the right of 0? Well, 0 is just a constant function. We're getting the limit of a constant function, and as we saw before, that's just whatever the constant function is, which is 0 in this case. Now we invoked the limit inequality theorem here. We have one quantity less than or equal to another quantity, and from that theorem the limit of both quantities are related in the same way. The limit of the left hand side is less than or equal to the limit of the right hand side. So we've established that f prime of c, whatever it is less than or equal to 0. We need to show that it's equal to 0. Now when we were constructing f prime of c, we divided both sides by positive h. So back up here we were actually assuming that h was greater than 0, some small positive value. But of course h can be negative. If h is negative, it doesn't change anything, since c is supposed to be a relative maximum. This result holds, so this inequality here holds. But now when we go to divide by h, we will be dividing by a negative quantity. So this will reverse the direction of this inequality. We're dividing both sides of this inequality by a negative h. So now we get this inequality here greater than or equal to 0 instead of less than or equal to 0. Now let's take the limit as h goes to 0 of the left hand side. Now since h is negative, h is approaching 0 from the left. It's some negative number and it's moving to the right towards 0. By the limit inequality theorem, on the right hand side we have limit as h tends towards 0 from the left of 0. And by the limit of a constant result, the limit of a constant is just a constant, where the constant is 0 in this case. But this limit here is nothing other than f prime of c. F prime of c is usually written like this: limit as h tends towards 0. So f prime of c exists, so this limit exists. So as before, if the limit exists, then both one-sided limits have to exist and equal f prime of c. So the limit as h tends towards 0 from the left must equal the limit as h tends towards 0 from the right. So if that's the case, the limit exists. So now we've established that f prime of c is greater than or equal to 0. So both of these results have to be true. The only way that both of them can be true is if f prime of c is actually equal to 0.